All right, in this video, we're going to talk about section 1.5 dealing with exponential equations. And in this video, we're going to be graphing exponential functions, describing transformations of the graphs of exponential functions, use the property of exponential functions to solve problems, solve higher order equations, solve applications involving exponential functions. So here we're going to introduce to you an important class of functions called exponential functions. All right, exponential functions are used extensively in modeling and solving a wide variety of real-world problems, like continuous compound interest, population growth, radioactive decay, and numerous other applications. Okay. Now, here's something where we deal with the same components, but it's going to be different functions here. The function f of x equals 2 raised to the power of x is different from g of x is equal to x squared. Here in this case, f of x is equal to 2 to the x, that's an exponential function, whereas g of x equal to x squared, that is a quadratic function in this case. So for the case of g of x equal to x squared, the variable is the base. But in the case of f of x equal to 2 raised to the x, your variable x is going to be the exponent. So now here's the formal definition of what a exponential function is. The equation f of x equal to b raised to the x, where b is greater than 0 and b is not equal to 1, your b is your base, has to be a positive constant other than 1 for it to be an exponential function. And for each different case, each different constant b, we call that b your base, as I mentioned. The domain of this exponential function is going to be the set of all real numbers. The range of this exponential function will be the set of all positive real numbers. So an exponential function is defined for only positive real numbers for its range. But the domain, of course, will be the set of all real numbers. Here's an illustration of the graph of an exponential function. The one on the top shows f of x is equal to 2 to the power of x. And it's drawn by connecting the points on the scatter plot with a smooth curve, as you can see here. Now, as you can see that the graph does level off towards the negative x-axis and increases as x increases. So here on the negative side, from negative infinity up to 0, here pretty much it levels off and then starts to increase. And then when it gets bigger and bigger and bigger for x, it just shoots off. Now, this one is g of x equals 2 to the negative x. Notice this is still an exponential function, but it's a little bit different here because this time it's leveling off towards the positive x-axis as x increases. All right. But as we go off to negative numbers, negative numbers get smaller and smaller and smaller. For g of x equals 2 to negative x, this part goes off, shoots off indefinitely. Now here's a theorem that deals with some of the basic properties of the graphs of the function f of x equal to b to the x. These graphs contain the point 0, 1, since b to the 0 is equal to 1 for any permissible base of b. So regardless of what the base b is going to be, the graph of the exponential function will always cross the y-axis at this point 0, 1. Because the y-intercept is, of course, the point where the graph crosses the y-axis when x is equal to 0. So when you replace your x with 0 here, b to the 0, with the exception of 0 itself, is going to equal 1. And the graphs are continuous curves. They have no holes in it, and there are no jumps or breaks in the curve. They're always going to be continuous. The x-axis is always going to be the horizontal asymptote. Okay, because as you can see here, the graph gets closer and closer to the horizontal asymptote. If b is greater than 1, then b to the x increases as x increases. And if b is between 0 and 1, then b to the x decreases as you let x increase. Okay. Now let's look at some examples of how to identify which of these graphs fits the ones that we have here. Here we got graphs F, G, H, and K. And we want to match the equation with the graph that's given here in the figure, like y is equal to 5 to the x. And sometimes it can help to put this in the calculator if you like. All right, so if I go to y equal to, let me clear the equation out. If I type in 5 raised to the x, I'll type in, press the number 5, press the hat key, and then xt theta n for the x. Okay. And what I would do here, I'd just go ahead and do the zoom 6 for the standard window. Might be a little bit hard to see with that, but if you want to change your window a bit, I would do this. I would go from -5 for the x min, +5 for the x max. X scale will be 1, but for y min, I will put 0, and then probably, let's say 10. And then x scale will be 1, and then press graph. And in this case, comparing this to one of these, it will have to be probably graph K. Okay, graph K would be the graph of y equals 5 to the x. And then part B would be y is equal to 0.5 raised to the x. So if I do y equal to, and let me store this in y2. I'm going to put in 0.5, press the hat key, and then get the xt theta for the x, and then do graph. Now notice that it's coming down this way. And that's what we have here. We got a graph of h coming out this way, and then it's coming down, getting closer and closer to the x-axis. So it looks like h will have to be, h will have to be the graph of y is equal to 0.5 raised to the x. And then next part C would be y is equal to 9 raised to the power of x. So in this case here, if I go to y equal to, now I'm going to put this in y3. So it'd be y and then the hat key. 9 and the hat key, and then x, and then press graph. This graph looks like it's coming more inward. So if you compare that to this, it would have to be graph F. And then pretty much the one that I didn't choose is graph G, which is going to be what part D is. Y is equal to 1/6 raised to the x. Now, if you want to verify that, you can just do y equal to, and then left parentheses, 1 divided by 6, and I'm storing this in y4. Left parentheses, 1 divided by 6, press the hat key, and then get your x by pressing xt theta n, and then graph. So yeah, it's this one coming downward and getting closer and closer to the x-axis. So it will have to be G. Okay, so that's how we identify or match those the graphs of those exponential functions. Okay. Now, example 2 looks like this. Graph the following function over the indicated interval. y is equal to 4 raised to the x. And the interval that they give us is from -2 to +2. Okay, this is what I would do here. And they do give us a choice of graphs to use here. So let's go ahead and press the y equal to button. Now delete all of these graphs and store that in y1. So here we got y equal 4 to the x. So we'll just type in the number 4, press the hat key for your exponent, and then press xt theta n for your x. So before, here's your hat key over here, and then the x. And I'm going to go to window. I'm going to press that button here and change the window here. Let's see, the x min, based on these graphs I have here for the choice of graphs that's given to me, I'm going to let x min be -3. X max will be 3. X scale will remain 1. Let's see. For the y min, I'll let that be 0. The y max, I have it at 25, so I use that. I'm going to use 5 as my y scale. Okay. And then press graph. Let's see what that graph is going to look like. Now let's compare that to the ones that we have here. And it looks like, obviously, graph A will have to be the best one to select. So I would choose graph A. Okay, that's example 2. All right, here's another example. Let's say we want to graph f of x is equal to -2 to the x on the interval from -4 to 4. All right, so here we go to y equal 2. Let's clear this equation out. The negative key is at the very bottom of your calculator. Press that, and then 2, press the hat key, xt theta n for your x. Now let's go to window. We're going from -4 to 4. So the -4 for your x min, x max will be +4, x scale will be 1. And let's do this. Since they have the y from -20 to 20, let's do -20 for the y min, y max will be 20. And I would go ahead and I'll do 2 for the y scale, just to be on the safe side. And then press graph. So we'll pick which one matches this. And by looking at it, it will have to be graph C. Has to be graph C. Because notice it's coming this way and then it's going downward. It's pretty much leveling off if you go in the negative direction, but when you go in the positive direction, it starts going downward. So here has to be graph C. Okay. All right, now let's look at example 4. This deals with the transformations here. Now we talked about transformations back in section 1.2. So do watch that video for that or review that video if necessary. Here we're going to describe verbally the transformation or transformations that can be used to obtain the graph of G from the graph of F. And in this case here, we got G of x is equal to e to the x and then -5, where f of x is equal to e to the x. So the graph of G is the graph of F, where it's shifted either up or down or to the left or to the right. How many units? Well, we got a function, and then we got -5 here. That -5 tells me the function f of x. So, and also you can do this. Since f of x is equal to e to the x, I can write this as g of x is equal to f of x -5. So we've got the f of x with the -5 on the outside. That tells me that there is a vertical shift. A vertical shift. So when there's a vertical shift, that means it's either going up or down. So that means if it's a -5, that means that it is shifted down how many places? In this case, 5 units. Okay. So the graph of g of x, which is e to the x minus 5, is the same as f of x equaling to e to the x. The only difference there is that the graph is shifted down 5 units. Okay. So do go back to section 1.2 and review those transformations that were discussed. All right, theorem 2 deals with the properties of exponential functions. For a and b positive, where a is not equal to 1 and b is not equal to 1, and x and y are real, here's our exponential laws here. These you should be familiar with. A to the x times a to the y is equal to a to the x plus y. If I multiply powers of the same base, I bring over the common base and add the exponents. The other one, a to the x divided by a to the y, that's equal to a to the x minus y. When I divide powers of the same base, I bring over that common base and then subtract your exponents. And then the next one down here is raising a power to a power, a to the x raised to the power of y. Anytime you raise a power to a power, you bring the base over and multiply your exponents. Okay. And this one, a times b, that product is raised to the power x. We take each factor inside the parentheses and raise each factor to that power. So it'd be a to the x raised times b to the x. And then a divided by b raised to the power of x. Here, a quotient to a power means that we take the numerator, raise it to that power, take the denominator and raise it to that power. So it'll be a to the x divided by b to the x. Now, number 2, this represents the one-to-one property. If you have a to the x equaling to a to the y, that's going to be if and only if your exponents are equal to each other. X is equal to y. Okay? We call that the one-to-one property for exponents. If your bases are the same here, I can set this exponent to be equal to that exponent and solve the equation. Number 3 is for x not equal to 0 and a to the x is equal to b to the x. That's going to be only if and only if a is equal to b. That means if these exponents right here are the same, then I can set these bases equal to each other, just like that. All right. Now note that -2 raised to the second equaling to -2 squared does not contradict property number 3 of theorem 2. The properties in theorem 2 applies when both a and b are positive. Right, so let's look at some problems like this one right here. Let's say we want to solve this given equation, 9 to the 7 minus 3x equals 9 to the 6x minus 3. Notice the bases are the same. That means I can set this exponent to be equal to that exponent. The bases are the same, so that means I can set this exponent to be equal to that exponent. So that means I have 7 minus 3x is equal to 6x minus 3. Here I'm just setting the bases to be equal to each other. And then we can go ahead and solve that equation. So in this case here, Let's see here. I'll move the minus 3x over to where the 6x is by adding 3x to both sides. And when I do that, I'm going to have 7 by itself is equal to 6x plus 3x. That's 9x minus 3. And then to get 9x by itself, I'm subtracting 3, so I need to add 3 to both sides of that equation. So that means that 9x is equal to 10. And then divide both sides by 9, you're going to get x is equal to 10/9. And I will leave that as an improper fraction. So x is equal to 10/9 will be the solution to that exponential equation. Okay. All right, example 6 is this. Let's say we got 8 minus 8 to the negative 5x minus x squared equaling to 8 to the 6. Now, in this case here, again, the bases are the same, so I can set this exponent to be equal to that exponent. So I can set negative 5x minus x squared to be equal to 6. Now, what I'm going to do here is move these two terms over to the opposite side since I have a quadratic equation. So when I move the minus x squared over to the other side, I'll just get x squared. And when I move the minus 5x over to the opposite side, I will get a plus 5x and then plus 6 equal to 0. What I'm doing there is adding 5x and adding x squared to both sides of the equation. Now, notice that x squared plus 5x plus 6 is a quadratic equation. I can factor that into two binomials here. So in this case here, x squared breaks up as x and x. And in this case here, factors of 6 that gives me 5x as a middle term would be a plus 2 and a plus 3. So I get x plus 2 times x plus 3 equal to 0. Then I set each binomial factor to be equal to 0 and solve. So I have x plus 2 is equal to 0, or x plus 3 equals 0. Each equation will solve for x. So for the x plus 2 is equal to 0, if I subtract 2, you'll get x is equal to negative 2. Or for the x plus 3 equal to 0, that means x is equal to negative 3. So my two solutions here will be x equal negative 2 or x equals negative 3. All right, now let's take a look at this equation right here. Here we're going to solve this given equation for x. Here I got x plus 10 quantity squared equaling to 2x minus 22 quantity squared. All right. Now to solve this, if we're squaring something, what we need to do there is take the square root on both sides. So we have to take the square root of the left side and the square root of the right side, but we also have to include that plus or minus symbol as well. So now the square root of x plus 10 quantity squared would just be x plus 10, equaling to plus or minus. The square root of 2x minus 22 quantity squared would just be, and I'm putting 2x minus 22 in parentheses. Because this means I have two equations that I'm going to need to solve for x. One of them will be x plus 10 is equal to positive 2x minus 22. The other one will be x plus 10 equaling to the negative of 2x minus 22. And notice that 2x minus 22 is in parentheses. So I have two equations that I'm going to need to solve for x. So that means I'm going to have two x values here. All right, now let's simplify this first equation here. Let's get the x over to where the 2x is by subtracting x on both sides. So that means I'm going to have 10 is equal to 2x minus 1x would just be x minus 22. Then to solve for x, we add 22 to both sides. That means I will have x is equal to 32. So one of my solutions is x is equal to 32. Now for the x plus 10 equals to negative of 2x minus 22, bring this x plus 10 down, but I'm going to distribute the negative over the 2x minus 22, so it'll be negative 2x minus times a minus, that'll be plus 22. And now let's get the variables on one side and the numerical terms on the other side. I'm going to move the negative 2x over to where the x is by adding 2x to both sides. So that means x plus 2x is 3x plus 10 is equal to 22. And to get 3x by itself, if I subtract 10 on both sides, this will be 3x is equal to 12. Divide both sides by 3. That means x is equal to 4. So my two solutions for this equation would be 32 and 4. Okay. All right. Let's talk about base e exponential function. An exponential function with a natural base e. So let's talk about that. One of the most useful values for the base of an exponential function is somewhat a surprise. If you examine most current calculators, there are keys for 10 to the x and e to the x. The value 10 is important because our numbering system is built on base 10. The value e is actually used more often than all other bases. Certain mathematical processes in calculus and advanced mathematics courses take on their simplest form when base e is used. The function with equation y equal e to the x is sometimes referred to as the exponential function. Okay. Now we can examine the natural base e. The base e is an irrational number, and like pi, it cannot be expressed exactly by any finite decimal or fraction, because any irrational number is a non-terminating, non-repeating decimal, and the natural base e is an example of that, along with pi. The base e can be approximated by evaluating the expression 1 plus 1 divided by x, the whole quantity raised to the x, for sufficiently large values of x. In other words, as you let x, the values of x get bigger and bigger and bigger, this expression will get closer and closer and closer to a certain number, and that number will represent the natural base e. And here's the table of that. So if you let your x value get bigger and bigger and bigger, then what's going to happen is when you evaluate 1 plus 1 divided by x quantity raised to the x, you're going to get closer and closer to what the natural base e is going to be equal to. And this is the approximate value for the natural base e, carried out to 12 decimal places. 2.718, 281, 828, 459, and it goes on and on and on without end. So this is an example of a non-terminating, non-repeating decimal, which is, of course, an irrational number. Okay. Now, let's look at the graph of an exponential function with the natural base e, and, of course, 1 over e. The exponential functions with base e and base 1 over e, or e to the negative x, respectively, are defined below. Okay. In both cases, the domain will be from negative infinity to infinity. The range, of course, will be from 0 up to infinity. And 0 is not included. Notice the parentheses. Because there's no value of x where e to the x will be equal to 0. We will talk about that in another video when we deal with logarithmic functions. So here's a graph of y equal e to the x, as you can see here. And of course, the y-intercept, of course, is always going to be 0, 1. And also e to the negative x looks like this. This is the graph in red. All right, now an application of exponential functions would be something like exponential growth and decay. Exponential growth and decay. Functions of the form y is equal to c times e to the k times t, where c and k are constants, and the independent variable t represents time, are often used to model population growth and radioactive decay. So in this case, if t is equal to 0, then y is equal to the constant c. And that is because if you replace the t with 0, you're going to have 0 times whatever k is will be 0. E to the 0 will be 1, and 1 times c will be c. So if t is 0, you'll get y is equal to c. The constant c represents the initial population or initial amount. The constant k is called the relative growth rate. And the relative growth rate is a percentage of rate per unit of time and is written in decimal form for the model. So they might give it to you as a percent, but you'll have to convert it to a decimal by either moving the decimal point 2 places to the left or taking that percent and dividing it by 100, which will give you the decimal amount of the decimal form. All right, here's an example of just that. Cholera, an intestinal disease, is caused by cholera bacterium that multiplies exponentially. The number of bacteria grows continuously at relative growth rate of 1.386. That is, n is equal to n sub 0 times e to the 1.386t, where n is the number of bacteria present after t hours, and n sub 0 is the number of bacteria present at the start. If there are 25 bacteria at the start, how many bacteria will be present, A, in 0.8 hours, and B, in 2.5 hours? So here's a two-part example. So that in 0.8 hours, that's your T. And we have 25 bacteria at the start. That's n sub 0. So now let's find out what n is going to be. N, of course, that's going to be n sub 0 times e to the 1.386 times t. And that 1.386 represents k, by the way, because k represents the relative growth rate. Now let's substitute some values here in that formula. So here we can find out what n is, which will be equal to n, that's 25, times e to the 1.386 times t, which is 0.8. And let's type this in the calculator. Let's see, second quit to get out of that. I type in 25. Now for the e, you have to do second and ln. Second ln gives you the e, because right above the ln key, you're going to see e to the x. To get that, you have to press second and ln. and then type in 1.386 times 0.8, and then press enter, you will get, and I'm going to say to 2 decimal places, 34.04. So after 0.8 hours, there will be 34.04 bacteria, I should say. Now, what about 2.5 hours, 2.5 hours? So now in part B, our T is going to be 2.5 hours. And N sub 0 is still going to be 25. So here we still use this formula, N equal to N sub 0 times e to the 1.386 times T. And then N in this case will be equal to N sub 0, which is 25. Then e to the 1.386 times T, which is now 2.5. And using the calculator, 25, second ln for your E, then 1.386 times 2.5, hit enter. To 2 decimal places, that would be 799.41. So that means there will be 799.41 bacteria after 2.5 hours. Okay. So that's just an example that deals with exponential growth. All right, next we'll look at exponential decay. Here's some concepts that deal with exponential decay. Cosmic ray bombardment of the atmosphere produces neutrons, which in turn react with nitrogen to produce radioactive carbon-14, or 14C. Radioactive carbon-14 enters all living tissues through carbon dioxide, which is first absorbed by plants. And then as long as a plant or animal is alive, carbon-14 is maintained in the living organism at a constant level. Once the organism dies, however, carbon-14 decays according to the equation A is equal to A sub 0 times e to the negative 0.000124 t, where A is the amount present after t years and A sub 0 is the amount present at time 0. Okay, so this is an example of exponential decay. We're going to use this right here to help us work this example. If 500 milligrams of carbon-14 is present in a sample from a skull at the time of death, how many milligrams will be present in the sample in 15,000 years? And let's say we want to round up the answer to 2 decimal places. So in this case here, we got 5,000 milligrams of carbon-14 present at the time of death. So that means A sub 0 is 500. And we want to find out how many milligrams will be present in that sample in 15,000 years. So T is going to be 15,000. And the formula that we're using, I'm writing that over as A is equal to A sub 0 times e to the negative 0.000124 times t. And notice that the exponent here is negative when you're dealing with exponential decay. Now let's substitute, find out what A is. A is equal to A sub 0, that's 500, times e to the negative 0.000124 times t, which is 15,000. All right, so using our calculator, we'll type in the 500. For the E, of course, second and LN. And then press your negative key for 0.000124 times 15,000. And then press enter. Now, if we round this off to 2 decimal places, that'll be 77.84. So that means in 15,000 years, 77.84 milligrams of carbon-14 will be present in that sample. So that's an example of just exponential decay. All right, next page is exponential regression. All right, sometimes the context of a real-world situation suggests that the change can be modeled with an exponential function. Current calculator technology allows analyzing observed data and obtaining a best fit regression model for the data. The resulting regression equation has the form y is equal to a times b to the x, where the values of a and b best fit the data set. Like in this example that we have here. The table at the right shows the number of internet hosts from 1994 to 2012. And in part A, we're going to let X represent the number of years since 1994 and find an exponential regression model, which is y is equal to a b raised to the x, for the number of internet hosts. And then part B, we're going to use that model to estimate the number of internet hosts in 2027. All right, in this case here, we need to do something here because this deals with X is going to be the number of years since 1994. We can't use these years here. We have to convert them as X values here. And what I mean by that is this. 1994 from 1994, for this one, it will be 0. 1997 from minus 1994, that's 3 years off. 2000 minus 1994, that's 6. 2003 from 1990 minus 1994 would be 9. 2006 minus 1994, that would be 12. 2009 minus 1994 would be 15. And then 2012 minus 1994 would be 18. Okay. Now, when we use our calculator, we're going to store these numbers in L1. The host, the number of hosts that you see here, that will be stored in L2. All right, so here we go. Using our graphing calculator. Okay, press the stat key right here. We're going to edit, so we're going to select number 1 for edit. We got stuff in L1 and L2. We need to clear this out. So what we're going to do here is go to L1 and use the up arrow key to highlight L1 itself. Press clear and then enter. Use my right arrow key to go over to L2. Use the up arrow key to highlight L2. Press clear and enter. Now I'm going to go back to L1 because in L1 I'm going to put in these numbers here, not the years, these numbers right here. Okay, because these represent X number of years after 1994. So that means the first one I put 0 and then enter. The next one will be 3, enter, 6, enter, 9, enter, 12, enter, 15, enter, 18, enter. Use your right arrow key to go to L2 and then enter the number here for the host in millions. You'll enter those numbers as is, 2.4, 16.4, 71.5, 158.4, 421.8, 587.1, and then finally 891.6, and then enter. Make sure that you enter these numbers correctly, otherwise your final answer will come off will be incorrect. And make sure that the same number of data values in L1 are, you have the same number of data values in L2 as well. Because for the first one, it corresponds to the second. All right, now in this case here, we need a exponential regression. So let's do this. Second and mode to get out of this. Then press the Stat key. Use your right arrow key to go to the Calculate menu. Now we need exponential regression. So I'm going to press my down arrow key to find EXPREG. That's exponential regression. That's the one I want. So I'm going to press Enter there. Let's see, X list. My X values are going to be in L1. They should be there. You should see L1 there. Y list should be L2. Okay, and then we're going to press that down arrow key to go to Calculate, and then press Enter. Now you see the exponential equation y is equal to a times b to the x. And they give you the a value, the values for a and the values of b. Now in this case, I'm trying to find out how many decimal places that they want. And in this case, let's say, yeah, they say 4 decimal places in this case. All right, so the exponential equation would be this. This for part A, that y is equal to the a to 4 decimal places will be 5.7200 times the b, which is 1.3739. And notice I'm putting this in parentheses. That's raised to the x. Okay. So that is the exponential regression equation for this model. Y is equal to 5.7200 times 1.3739 raised to the power of x. Now, part B, we're going to use that model to estimate the number of internet hosts in 2027, I'm sorry. So X represents the number of years after 1994. So we're dealing with 2027. We need to subtract 1994 from 2027. So 2027 minus 1994 would be 32. No, 33. So X in this case will be 33. That's 33 years after 1994. All right, in this case here, here's our formula. So we have y is equal to 5.7200 times 1.3739 raised to the x, so x is going to be 33. Okay, and in this case here, we're going to round to the nearest whole number in this case. So in the homework, you have to do exactly what they ask you to do when you're rounding your answers. So 5.7200, and then left parentheses, 1.3739, close parentheses, press the hat key, then 33. So to the nearest whole number, it would be okay. Well, since I've rounded these off to 4 decimal places, this is what I come up with to the nearest whole number, 204,134. Because the last three, this 8 makes that last three a 4. So in this case here, the estimate number of internet hosts in 2027 would be 204,134. Okay. All right, the last thing we'll look at in this video will be compound interest. The fee paid to use another's money is called interest. And interest is usually computed as a percent, called the interest rate, of the principal over a given period of time. If at the end of the payment period, the interest due is reinvested at the same rate, then the interest paid on interest reinvested is what we call compound interest. If a principal called P, which is your present value, is invested at an annual rate called R, which is expressed in the form of a decimal, compounded M times in a year, then the amount A, or the future value in the account at the end of T years, is given by this formula. A is equal to P times the quantity 1 plus R divided by M raised to the M times T. And if you probably had college algebra before, you probably seen this formula written in a little bit different way. Here they're using M here instead of the N, where N is the number of compoundings. Here we're using M as the number of compoundings in a year. All right, so in this example here, in finance, suppose that $2,500 is invested at 3.7% annual interest rate, compounded monthly. How much money will be invested in the account in A, 4 months, B, 8 years? Now, I need to warn you that time is usually going to be in years. So in part A, you're told 4 months. So that means our T has to be 4 months divided by 12. Because there are 12 months in a year. And T has to be the time given in years. So in this case here, 4/12 in simplest form will be 1/3. So your time will be 1/3. And we also have something else, a $2,500 investment. So P is $2,500. The interest rate is 3.7%, but we need to convert 3.7% to a decimal. You can do this by doing 3.7 divided by 100. That would give you 0.037, because the interest rate has to be in decimal form. And it is compounded monthly, so that means your M is going to be 12. Because there are 12 months in a year. And here we use that compound interest formula. A is equal to P times 1 plus R divided by M raised to the M times T. And then we just substitute here. A is equal to P, that's 2,500, times 1 plus R, which is 0.037, divided by M, which is 12. That's raised to the M is 12, times T, which is 1/3. But let me go ahead and multiply 1/3 times 12, which is, of course, 4. So A is equal to 2,500 times 1 plus 0.037 over 12. 12 times 1/3, or 12 over 1 times 1/3 will be 4, because that's like 12 divided by 3. Now we can type this in the calculator. And in this case, it would do 2,500. Then left parentheses, 1 plus 0.037 divided by 12, close parentheses. For the exponent, press the hat key and then 4. And then press enter. We're dealing with money amounts, so we're going to have to round this off to 2 decimal places. So this will be $2,530.98. $2,530.98. Okay, so the amount of money that will be in the account in 4 months will be $2,530.98. So that's part A. Now, part B, in 8 years. So we want to find out how much money will be in the account for 8 years. Well, this is already in years, so we can just say T is equal to 8. Okay, and then use that same compound interest formula with those same values here. So here's the compound interest formula again. P is still $2,500, so now 2,500 times 1 plus R, that's still 0.037 divided by M. There are 12 compoundings in a year, so your M is still going to be 12. And that's going to be raised to the M, which is still 12, but this time T is going to be 8. And if you want to, you can do 12 times 8, which is 96. So the A is equal to 2,500 times 1 plus 0.037 divided by 12. That's raised to the 96th power. And then enter that in the calculator. So 2,500, then left parentheses, 1 plus 0.037 divided by 12, close parentheses, then press the hat key for your exponent, 96. To 2 decimal places, that would be $3,359.65. That would be the amount that would be in the account for a $2,500 investment at 3.7% compounded monthly after 8 years. All right, now the other part of that is continuous compound interest. The concept of continuous compounding is that the frequency of compounding is increased infinitely so that at every instant in time, interest is computed and added. Recall that the base E of the exponential function is found using increasingly large values of x in this expression, 1 plus 1 divided by x, and that quantity is raised to the x power. When a principal amount P is invested at an annual rate called R, and is compounded continuously, then the amount A in the account at the end of T years is given by this formula. A is equal to P times e to the RT. And of course, E is your constant. That's the exponential function base. Okay, so you've probably seen this again in college algebra as well. But let's say we had this example. Find the value of an investment of $20,000 for 13 years at an annual interest rate of 4.55% compounded continuously. So here we have a principal of $20,000. The time is 13 years, and it's in years, of course. The annual interest rate of 4.55%. Now, we need to convert that to a decimal. Let's say 4.55, divide that by 100, would be 0.0455. So your rate in decimal form is 0.0455. And here's compounded continuously, so we must use this formula: A is equal to P times E to the RT. And your P in this case is $20,000 times E to the R, that's going to be 0.0455 times T, which is 13. Now this we can just type in the calculator directly. So in this case here, I'm going to type 20,000, and then second and LN for the E, and then type in 0.0455 times 13, and then hit enter. Now the two decimal places, this will be $36,133.93. So that amount represents the value of an investment of $20,000 for 13 years at an annual interest rate of 4.55% compounded continuously. Okay. And that will conclude this video in section 1.5 dealing with exponential functions. Feel free to email me or reach out to me if you have any questions about any of the problems presented in this video, or if you have questions about the homework in my math lab about this section 1.5.